challenge was to draw heating and cooling curves for dry ice. I'm going to do this on two different smart screens so that I can make it big enough. Dry ice is going to have some different properties, and we're going to have to look up what those are. Hopefully you know enough about dry ice to understand that when it melts, it doesn't turn into a liquid. It turns directly from a solid to a gas. We have to find out the temperature that it does that at. Right here I find some information. It's either at the number negative 109.3 degrees Fahrenheit or negative 78.5 Celsius. This science class, I'm going to choose the Celsius. So about negative 80 just makes it easier for me to write on my screen. So there's going to be a magic number at about negative 80 degrees Celsius. So what happens when you warm up dry ice? Well, you put it in the room and it actually does warm up until it melts, and then it turns directly into a gas, and then it can warm up to a higher temperature. Dry ice is simply carbon dioxide in its solid form, but it doesn't melt into a liquid at our pressure. So here is my heating curve. My cooling curve would look very similar. It's going to also have to have the magic number negative 80-ish degrees Celsius. But this is going to be its cooling off until it gets to that plateau when thermal energy, or when the energy that goes in is just simply changing its phase, and then it can cool off some more. These flat plateaus are phase changes. In this case, it doesn't have a great name because we are making it directly go from solid, or from gas to a solid. How would that be accomplished? Lots and lots of pressure. It's done under pressure. I want an LOL for this area, an LOL for this area, and an LOL for this area. So this has three plateaus or three segments instead of five, because water had five, because it melts and it vaporizes. So we've got, well, a lot of thermal energy. We'll call that 2 bars. And as it cools off, it's going to get down to not much thermal energy, 1 bar. I wish I had saved room. If I was going to write the system inside there, I would have written dry ice, dry ice, dry ice. That's what we're paying attention to, the carbon dioxide. This is the cooling curve. So I'm going to have heat exit. But it's going to, while this is happening, it's staying in the same phase. That's a gas. Gas has 4. And when we're all done, it's still a gas at that segment. And so it also has 4. Net change of 1 bar of energy. It is cooling off, so that 1 bar of energy is leaving the system. The next one is a flat spot, meaning if we ended up right here with 1 thermal energy, wish I would have rethought that, but that's okay. I'm going to change this. I'm going to go back and change this to 3, and then this to 2. That way I don't have to change my net effect. That means I can start with this at 2 and end with this at 2. There's no right or wrong answers, but I don't want to deal with half bars. So in this case, the thermal energy is going to stay the same. It's the phase energy that will be changing. It is changing from a gas, which has, like we just mentioned, 4 bars. But when we're all done, it will be a solid, and solids only have 1 bar. That's a net change of 3 bars, and that's exiting the system. We have to get rid of that energy to turn it into a solid. Once it all becomes a solid at negative 80 degrees Celsius, which is a really, really cold temperature which damages your skin, then we could actually cool it off some more. We could change to thermal. I know negative 80 shouldn't have a lot of thermal energy, but it's all relative. It can still get much, much colder, and I'm going to make that go down to 1 thermal. But the phase is still going to be solid, and so this 1 bar of solid phase energy still will be 1 bar of solid phase energy. Once more, we are exiting 1 bar of energy. Why does it how do I know that it's exiting? It's cooling. In order to cool it, we have to remove heat. I could go back to this side and do the same types of things. And it's really just going to be the reverse of what we just did. This is for the changing part, the one that has the change in temp. This is for the plateau. And then this once more over for here, L, O, L. So realistically, I'm going to end up drawing the same three as these. The big difference will be just the direction of the arrows. The heat will have to go into the system in order to melt it. So I won't go through all the steps of that, but that's kind of the same idea.